let's say between the network and data link layers, let's stay there a little bit, right? And as we continue looking at the ARP process. Using this ARP table, let's see how the ARP process would get us this ARP table entry for the default gateway. Let's start with this little setup. We have a switch and 2 laptops and a router connected to it. Our laptop knows the IP address of the default router for DHCP, but not the physical address yet in this scenario, right? So our laptop is going to send out a broadcast to every device that's connected to through an ARP request. So the ARP request here is what's 192.168.1.1's MAC address. So this is the initial ARP request. The switch is a layer 2 switch, meaning it can't read IP addresses, only MAC addresses. So the switch sends out an ARP request of its own, asking all the devices it's connected to, are you 192.168.1.1? So the ARP request, as I mentioned, gets sent to every device connected to the switch, except for the one where it received the initial ARP request from. So now the router is like, hey, that's me. I'm 192.168.1.1, and here's my MAC address. So the router sends an ARP reply back to the switch. Then the switch sends the ARP reply back to our laptop with the default router's MAC address, which is then placed into the ARP table cache on the laptop. So before the switch sends the ARP reply back to our laptop, it makes an entry in its MAC address table. So this entry says which MAC address is connected to which switch port on the switch. That way, if your laptop wants to send more data to the other device later, it knows exactly which port on the switch to send it to. These are MAC addresses from ARP replies. These are simulated MAC addresses, so no reason to hide these. Notice that the type here is dynamic, so these will be forgotten at a later date. And these here are the switch ports that receive the responses to the switch. So the switch now knows which switch port to relay data that is headed to these MAC addresses. So now let's dive into the data link layer. Remember that PDU has now become an IP packet since passing through the network layer and getting the IP source and destination header. Well, now in the data link layer, our IP packet will go through another transformation. If we take a look at what happens to our IP packet in the data link layer, you'll notice that there is now a new header here and a new footer. The data link frame header adds the source MAC address, which is our laptop, and the destination MAC address, which is the default gateway, to our IP packet. At the bottom of our IP packet is a footer or trailer, which has been added. So in a trailer is a frame check sequence number, or FCS number. This FCS is used to check for errors in the data. The number is calculated based on the data, and then the number is recalculated when the receiver gets the data. So if the numbers match, then the data is good. So what do these new data link layer additions transform our IP packet into? The data link header and trailer make the IP packet into a layer 2 frame. Let's stay here in the data link layer to learn how this layer 2 frame will travel to its destination. So the switch receives our layer 2 frame and reads the destination and source MAC address from the data link header. The switch then reads its MAC address table to see what port has the destination MAC address assigned. The switch then sends the frame to the switch port the destination MAC address is on, which here is FA0/1. Now we finally made it to the physical layer. Here we start with our frame, which has headed to the switch port on the switch that the default router is connected to. Once it reaches the Ethernet cable, another transformation happens. The frame converts into bits, Bits, like you hear in gigabit Ethernet, actually stands for binary digit. So binary as in 2 digits. That's because bits are either 1 or 0. Those are the only 2 digits a bit can be. The zeros represent off digits, and the ones represent on digits. So why are we worried about bits? Because the frame gets distilled down to its bits in order to travel. These are a few different transmission types our bits can travel through. One transmission type is through copper wires like Ethernet and coax cables. When sent through copper wires, the bits are translated into pulses of electricity, with ones represented by an electrical pulse and zeros represented by gaps in electrical pulses. Think of it like Morse code. Another transmission type is fiber cables. Instead of electrical pulses, we have light signals, with one being a pulse of an LED or laser light, and a 0 being a gap in light pulses, and so on. Lastly, we have the wireless signal transmission type, like Wi-Fi or Bluetooth. For bits in a wireless signal, a high frequency would represent a 1, while a 0 is represented by a low frequency signal, and so on. Wireless transmissions may also use other characteristics of wireless signals, such as the amplitude or phase, to represent zeros and ones. Depends on how it's configured. Our frame will now travel from the physical layer back up to the data link layer as it travels to our default router. Our frame, now bits, travels across the copper Ethernet wire as electrical pulses of zeros and ones, which then reach the default gateway router, being placed back into our layer 2 frame. After checking the frame check sequence number, FCS, of our frame and making sure that it's all good, the router removes the data link header and trailer to look at the IP packet's source and destination IP. Of course, removing the data link header and trailer transforms our data packet back into an IP packet. This brings us back up to the network layer. Once the router is able to see the IP packet, the router checks its routing table and gets the destination IP address of the IP packet. Right? So that's what we're mentioning here. Here's the routing table. And this is where it's checking for the destination IP. So since the destination IP is not in the routing table, the router is going to send its data to the gateway of last resort for data traffic that is headed for an IP address not known by the router. So gateway of last resort right here, this is where it's going to send any of these packets that it just doesn't know where the destination is, because it's not in here in the routing table. So as I mentioned here, since the destination IP is not in the routing table, it's going to send it to the gateway of last resort, and which is the default route for data traffic. The gateway of last resort is like the default router of a router. So the IP you see as the gateway of last resort is actually the interface that will forward the data to the next router, as the next router is connected to this interface here. So we still have a few things we need to do before we leave the router, so let's stick to the network layer. Let's check our source IP and destination IP again. Here we have our source IP, the IP of our laptop sending the data request. And here we have the source port from the application layer. This is the port ID given to the browser tab where we made the website data requests. If you look at our source IP, you'll notice that it's a private IP. It's in class C range of private IPs. But how are we going to get our private IP, which does not appear on the internet, to reach the destination IP, which is a public IP on the internet? That's where network address translation, or NAT, comes in. Using NAT, routers translate private IPs into public IPs so the data can be routed out to the internet. Here's a look at the NAT table on our router. Here under Inside Global is the IP of our laptop translated or NATed to a public IP address by the router. Think of Inside Global as the global internet address inside the network. Under Inside Local, you see our laptop's normal private IP address. Inside Local is the private IP address inside the network. Under Outside Local and Outside Global, you can see the next router the data will be sent to. Think of Outside Local and Outside Global as in how we're going outside the local private network and into the global internet using this next router. So now that we've used NAT to translate our IP packet, how do we get our NATed IP back into a frame to get to our router's gateway of last resort, which is our router's next hop? For that, we have to look at our router's ARP table, because our router, like our laptop, matches the MAC address to an IP address, but it also matches the MAC and IP to an interface like a switch does with its MAC address table. Think of the router's ARP table as a combination of our laptop's ARP table and our switch's MAC address table. Let's take a look at our router's ARP table shown at the top and our router's IP routing table shown at the bottom. Here we see the gateway of last resort was set in our router's routing table. And at the top, we see the IP's MAC address as well as the port that the default gateway router is connected to. The only two times an IP is NATed is when a private IP needs to be translated to a public IP to travel the internet, or when a public IP packet needs to turn into a private IP packet to get back to a computer on a local private network. Let's take a look at our NATed IP packet source and destination ports and IPs. Our source IP was changed to a public IP, but our source port actually stayed the same. Our destination IP and port stayed the same as it was already a public IP. If our router was receiving a response from the web server, our router would receive an IP packet where the source IP would be the web server's public IP and 443 port, and the destination IP would be our NATed public IP address. In that scenario, our router would have to translate the NATed public destination IP back into our local computer's private IP. Now that we have our NATed IP, and we know which router the port the default gateway router is connected to, let's turn our NATed IP packet back into a frame at the data link layer. To turn our NATed IP packet back into a frame, our router encapsulates it with a data link header with the source and destination MAC address, along with a data link trailer with the FCS number. Our router gets the default gateway IP from the IP route table and then looks for the IP in its ARP table to get the MAC address. That's how our router knows the default gateway's MAC address for the destination MAC address in the data link header. From there, our router sends a newly formed frame off to the router port connected to the default gateway router, which it found from its ARP table. Now onto the physical layer to transmit our packet to the default gateway of our router. So now our frame is going to once again be transmitted as electrical pulse bits through the copper Ethernet wire, getting to the default router and becoming a frame again so the default router can read it.